Hello everyone, I'm Chiu-Hsuan from National Chiao University. I'm glad to be here to present our work, HapticSphere, physical support to enable precision touch interaction in mobile mixed reality. This work is done with Chen-Yuan from NCTU, Neng-Hao from NTUST, Andrea Bianchi from KAIST, and my advisor Liwei from NCTU. Let me introduce HapticSphere with a short video. HapticSphere is a system that integrates a finger tracking device with a passive string. This provides physical support at the user's finger for immediate touch interaction in mixed reality. Let's talk about our motivation. Touchscreens provide physical support for finger during touch interaction. This helps user with haptic feedback and a form of finger stabilization on the go. However, current mixed reality in-ear touch input does not offer such physical support, and this may lead to lowered performance. Hence, we present HapticSphere, a system that integrates a finger tracking device with a passive string. This passive string forms a solid spherical wall surrounding the user. The user perceives physical support at the finger when reaching the maximum extension of the string. This support provides both stabilization and haptic guidance for touch interaction on the go. Here, we provide a scenario of HapticSphere on mobile mixed reality. In the beginning, Steve is watching a video in virtual reality. His friend Jeff texts him to meet him for lunch. After replying the message, he switches to mixed reality mode and moves on. Here, we simulate the walking situation with a treadmill. Now, Jeff texting again for lunch advice. So, Steve types in the word steak on the go with HapticSphere for searching the restaurant. After that, he reserved a restaurant for their meeting. Finally, he meets Jeff happily. So here, it can be seen that the main challenge of the touch interaction is that the unconstrained hand motion makes the touch precision low while the user is walking. Our main goal is to support precise touch input selections in mobile mixed reality. To achieve the goal, we present HapticSphere to produce solid force feedback on the fingertip that enable the physical support for precise touch interaction. HapticSphere hardware consists of a mobile HMD capable of 3D finger tracking and a passive string connecting the user's finger to the user's body. The physical support from the string provides stabilization, thus improve the touch precision when walking. Here, we review works that enable wearable force feedback as well as string-based haptic interactions. Hand-scale force feedback such as HapLink and Wolverine is primarily achieved with handheld controllers and wearable interfaces. In finger-scale feedback such as gravity grabber and hap thimble, they simulate the features of a virtual object on the finger. These works provide localized force feedback on the user's fingertip or hands, but they are unable to constrain the rest of the body or the arm's motion. String-based interfaces can both limit or assist wider motion involving the arms or other body parts. With an active braking mechanism, they allow rendering force feedback on the user's finger or hand automatically. On the other hand, elastic arms employ flexible passive string to constrain the full motion of an entire arm. Now, I would like to present HapticSphere for you. We present 3 different ways to attach the string to the user's body: direct attachment to the HMD device, to the neck through a neck strap, or to the shoulder through a backpack strap. Among these 3 attachment methods, but HMD is constrained to head, while the other two methods are not. Since the by-neck and by-shoulder strings are not constrained to head, the relative motion between the attachment point and the HMD is required to be captured. Instead of modeling the head motion, we present a new approach that utilizes head-coordinated touch interaction to estimate a grand haptic sphere. With the phrase head-coordinated touch, we mean that the user would aim at the target with the heading while touching the target. This removes the degree of freedom generated by the head motion. Here, we demonstrate a user estimating a grand haptic sphere by head-coordinated touch interaction. The touch points are collected in the calibration process to estimate the sphere. To sum up the grand haptic sphere, it works for all attachment methods and makes the calibration in single process. Thus, in the later interaction, the user will perform the touch operation with head-coordinated touch as well. For more detail, please refer to our paper. To validate the grand haptic sphere and understand the benefit of physical support for touch interaction, we conducted two user studies. In study 1, we want to evaluate our calibration procedure. The study followed the within-subject design with one independent variable, interface, which consists of 4 conditions: by HMD, by neck, by shoulder, and no support as a baseline. Participants will first acquire a grand haptic sphere, then perform the target acquisition test with head-coordinated touch. In each condition, participants will first calibrate a haptic sphere in head-coordinated touch interaction. Once the calibration is done, participants tested the system for few trials to ensure the calibration was correct. After the calibration, a crosshair is rendered in each trial, and participants will acquire a target in head-coordinated touch as accurately as they could. So here's the result. We can see that without physical support, users encounter overshooting a target in depth, while physical support helps prevent the finger overshooting the interface. Hence, we confirm that the participant completed the study with physical support in all attachment methods. Here, the average precision showed that there were no significant difference in these 4 cases, indicating that users performed target acquisition equally well without problems. Also, the precision touch chart suggests that the effective button size is 22 by 22 millimeter. And since the by HMD interface showed the best touch performance in terms of precision and overshooting distance, we adopted by HMD interface and the button size to the next study. Next, we want to understand how physical support assisted users in target acquisition during sitting and walking. The participant will perform target acquisition with 3 independent variables: mobility, haptics, and button sizes. Mobility consists of sitting or walking. Haptics consists of with and without support. Button size consists of 4 button sizes. The mixed reality mode was enabled by blending 3 layers of image together, including context layer, stereo hand layer, and graphics hand layer. This allows the user to interact with our interface when walking on the treadmill. After the calibration, a training section was provided in the walking condition to make sure the participant familiar with the treadmill speed and was comfortable to interact with the interface. After the training section, participants started performing the target acquisition task. So here's the result of study 2. First, the physical support does not benefit in error rates when sitting, but it significantly reduced error in the walking conditions. We further examined error rates in sitting and walking conditions against button sizes. Only a borderline difference was found in the sitting condition, but a significant difference was found between buttons in the walking conditions. This indicates that the impact of the mobility on button sizes was mainly relevant in the walking condition. Hence, we compare the physical support against the button size in the walking condition. significant main effects of both haptics and button sizes were found, indicating that the physical support outperformed node support under the working condition. From the result, it can be seen that the physical support stabilized mediate touch effectively and improved the touch accuracy in the working condition, which matches our main goal to enable precise touch interaction in mobile mixed reality. Now, I would like to discuss some features that can be improved. In our implementation, we use Leap Motion as our finger tracking device. Hence, the effective button size might be affected because of the tracking performance. Also, the limited field of view causes the user's hand should be placed in front of the Leap Motion view, which limits the interaction space. Our current prototype may prevent the user from lowering his or her hand during the interaction. Therefore, we present a new design that uses the retractable rail body as the graspable part. The rail retracts to the home position automatically when releasing it, which allows to fast engage and disengage the interaction. The perceived haptic property of physical support depends on whether the string is rigid or flexible. However, since the visual interfaces do not need to mimic the physical stiffness perfectly, by applying the haptic retargeting techniques like Spark's haptic proxy, we can allow the visual channel compensate for inaccuracy in the haptic rendering, which is our future work. So to sum up, we have presented HapticSphere, a wearable string-based interface that provides physical support and feedback for in-ear interaction during mixed reality. With 2 studies, we demonstrated that physical support enables precise touch interaction using mid-ear selections in mobile situations. So thank you for listening, and I'm happy to take any questions.
We have time for 1 or 2 questions. Yes, please.
Hi, it's Michael from University of Bremen. That was a great presentation, nice work, thank you. Did you consider having an adaptive length of that string so that it can be extended or shortened if I want to do something right here or up there or let it hang free?
Oh, yeah. So that's a great question. So actually, we have also that actually is one of our future work that we actually consider it that with 2 depths to enable like near interface or far interfaces. So, but actually in our work, we actually focus on enabling physical support in touch accuracy to enhance the touch accuracy. So that's a great suggestion. Thank you.
Hi, Doug Bowman from Virginia Tech. Have you guys tried any other interactions just besides just button pressing? So have you tried dragging, scrolling, drawing, any other sort of more subtle interactions?
Oh, thank you. So yes, actually we have tested for some others interactions, but not in this work actually. So in this, we'll just focus on this part. But yes, we have actually done some, for example, drawing or writing on the interfaces. Yeah, thank you.
And how well does that work?
So actually, it depends on if you want to drag. It depends on the spherical, and it might be you have to have a better tracking device, since the Leap Motion might do some tracking performance. Since it might be, there's some mistake if the tracking, that it may be things that your hand is not on the surface. But if you have a better finger tracker, then it can be enabled.
Okay, so let's thank the speaker again.